Lecture 49, Significance Revisited. Want to just make explicit a little more some things that maybe I kind of hinted at in the last lecture and some other lectures. So, we've seen how hypothesis testing is used to test claims about population means. In coming lectures, we'll see hypothesis testing for claims about other population parameters. But first, what I want to do is take a few short lectures to add a few more useful concepts to the whole idea of hypothesis testing. So in bold there I say, sometimes a hypothesis test may have no apparent significance level associated with it. This should not necessarily seem strange, as the significance level it provided is not some property of nature, but instead is simply a contrived cutoff probability for determining unusualness of our sample statistic. A smaller significance makes it harder for us to declare a sample statistic to be unusual, and hence to reject the null hypothesis. Smaller significance means the critical value is farther out, this way or that way or both. So your test statistic has to be more extreme to get in the rejection region, right? And the significance level is often just artificially stated. I want this to be my cutoff level, right? There's nothing in nature that necessarily suggests the significance level should be at one level or another. So then I say, without a significance level, if you're just faced with the problem and you have to make a decision, you have to formulate a null and alternative hypothesis and decide, are you going to reject the null or fail to reject the null? You have to have some criterion for deciding. If they do not give you, if you're not given a significance level, then I say here, without a significance level, then it is crucial to compute the p-value of the test statistic. All right? If you think about that, well, then I say, and then make a judgment call on whether to reject the null, on whether to conclude your result is statistically significant, in other words. If you think about it, that's really what you want to do, because you're going to have, let's just say it's a right-tailed test. I don't have a cutoff, right? I don't have a critical value. But my p-value for my test statistic will tell me the tail probability associated with it. If the p-value is very, very small, that means I'm way the heck out here, right? Small p-value, here's my test statistic. All right, if it's small, I'm more inclined then to reject the null. If instead it's actually back here, it's big, if the test statistic is back here, and my p-value is big, and that's what I would be computing. I'd be computing the p-value to be big and then concluding, oh, my test statistic is in close enough that I don't necessarily feel like I can reject the null hypothesis, right? The value is not so extreme. All right, I give an example then. And that example says, suppose the degrees of freedom are 56. So you're performing some test. Degrees of freedom are 56. The t-score is 2.08, and we have a one-tailed test. So let's look at that. So this is t degrees of freedom equal 56, and it's a one-tailed test. So it's, let's say, a right-tailed test. So I get a test statistic of 2.8. So here's my my test statistic equals 2.08. All right, it says we compute the p-value to be 0.021057, and I say you should be able to get that using your favorite technology. We talked about using a website I gave you, and there, if you have another way of doing it, that's fine. If you try to look up on a table, you're probably not going to find it, right? Because you won't have a critical value that's exactly equal to that value for that degree of freedom, that you just happen to get the right tail probability. So you have to be able to get that. Make sure you can get it. 0.021057. All right, so this is my p-value, the tail probability associated with my test statistic. Okay, so I say here we might conclude maybe we would conclude the result is statistically significant. Statistically significant. And what I may be thinking there is I may be thinking in my head, though it's not stated, I may be thinking at the 5% or 2.5% level, for example, right? Or the result is not statistically significant. Maybe thinking at the, why is it significant at the 5% or 2.5% level? Because 5%, 0.05, would have a bigger area, and so I'm thinking back here for my cutoff, 2.5% would still have a bigger area because that's a little over 2%, right? So if I'm now going to think that it's not statistically significant, the test statistic doesn't lie far enough out, then I need smaller tail areas for my cutoff value for unusualness, for my significance. So I may be thinking at the 1% or 2% significance level, right? So I could, depending on what I'm thinking of, I could say it is significant or it isn't. And usually what you want to do when you're, if you're actually a researcher and you're presenting these results, you would give the p-value, and I'll talk about this in a minute, but you would perhaps pick a, if you don't give the p-value, you should say then that it is statistically significant. If you want to say that, then you better give a cutoff level. You better introduce it's statistically significant at the 5% level, or it's not statistically significant at the 2% level. You better kind of say what you're doing, but more often what you really say is, okay, but down at the bottom I say, recall our grip strength example. The test statistic was -8, so it's going to be statistically significant at very low levels of significance, right? That's a pretty big one. And if you put that in a p-value calculator, you'd get a very small value for your p-value, tiny, tiny tail area there. And what you say then, see on the top of the next page, when reading research, you might see something like, so if I don't give you the p-value, I should say kind of what my cutoff level is, but better off I should just give you the p-value. So I'll say something like, maybe in my research I find that the results were, you might see like the phrase highly statistically significant. Statistically significant. And then I better say what I mean. So what happens is you'll see in parentheses, the p-value, they'll just say capital P meaning p-value, it's small, it's less than whatever, 0.0001 maybe. All right, that would be a very typical thing you would see. And of course, what are you doing here? You're rejecting H naught, right? This is where you reject H naught, right? Okay. And some folks take issue with the phrase, the adverb highly there. It's either statistically significant or it isn't. But that's people who have set a cutoff, right? If what you have is a test statistic that's way, 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 way the heck out, what you're saying is that, hey, you can set that cutoff kind of almost anywhere you want, and it's still going to be statistically significant. So we see the word highly statistically significant coming in. Or you might see something like this. Results were not statistically significant. And then I better tell you what I mean by that. And maybe I computed my p-value to be about 0.23. Okay, most anyone who looked at that p-value would say, oh yeah, statistically significant. That's a very small tail probability on your test statistic. Most people looking at that one would say that's not statistically significant. Your test statistic is in too close to the mean. It's in too close here. I've got such a big tail area. I got almost a fourth of the area in its tail. It's in too close. It's not statistically significant. Of course, here we're failing to reject, right? Failing to reject H naught. All right, and this one, as I think I've said before, this one here doesn't mean H naught is true necessarily, right? Necessarily. Am I going to get that all in here? Pretty much. A larger sample size can, you can write this down if you want, a larger sample size could push a result into statistical significance, all right? And we saw that in the example, I think it was lecture before last, where we started with a small sample and we got a result that wasn't statistically significant. But if all the numbers stayed the same except the sample size was larger, same sample mean, same sample standard deviation, the larger sample size caused us to be able to say that those results, the same numbers, actually gave us a statistically significant result, because when you convert to the t-score, it actually pushed the test statistic way out and gave it a small p-value. So I just wanted to reemphasize that here. But the main thing here is that in the real world, you often aren't handed, here's your significance level, right? Then what you have to do, after you've done your test, you compute your p-value and you make a call. Right, you make a call, and maybe you state it like this. If you have a really low p-value, there you go. If you have a big p-value, then you'd say that the results are not statistically significant. I have personally done work where I got a p-value on the order of 10%. 9% I think is one example I had in some work. And so it's statistical significance is somewhat dubious, right? It's still got kind of a small tail probability, but not a real small tail probability. So if I report the p-value, then the reader can kind of make the conclusion that they want to make from that, right? I don't have to insist it's statistically significant or it's statistically insignificant. They can kind of see from that p-value, and they can make a judgment call.